Hello everybody, Blake here again with another installment in this series about spacetime particles, where we're trying to basically use a medium that defines spacetime to solve some of the more uncertain theories, or at least simplify some of the more uncertain theories that we have out there to explain some of the physics phenomenon that we're observing. In this particular episode, we're going to talk about the double slit experiment, and we're going to try to come up with a model that does, that explains the phenomenon of what we see without any sort of magical phenomenon. And we'll get into what I mean by magic later. So, what we'll be covering. First, we'll just do a quick review on the double slit experiment and how it works with the de Broglie wavelength. And most of this whole episode is going to be looking at particles. We'll talk about light a little bit, but really I'm more interested in like if we were to use an electron through the double slit experiment. Then I just want to review what kind of requirements we would need to make this experiment work using just physical mechanisms. And then we're going to do a couple simulations and see if we can get this to work. And so, again, we're just going to do a quick review of the double slit experiment, and particularly for particles or something. But yeah. So the double slit experiment can be done using particles or photons. And so essentially what we have is some sort of launcher gun that is firing particles or photons out. And then we have some double slit, and the distance between the slits would be D. Then we have some sort of detector. There'd be like some distance L here. But classically, what we would expect is the particles would go through the two slits, and we would expect two big dark bands behind the slits. Imagine you're throwing baseballs or golf balls through. They're just going to basically land behind the slits. However, if we actually perform this, let's just say, if we perform this with photons or electrons, it doesn't matter if you do one particle at a time or a lot of particles at the same time, but as the signals on the detector build up, you start to get what we call an interference pattern. So you get one large band and then a slightly, maybe the spacing is not quite this way, but, and so essentially you can imagine that this would be intensity curve here. Drawing, challenging. These should go down to 0. But anyway, what you would expect here is that you get the large intensity in the center, and then you get these bright spots, then dark spots, bright spots, dark spots. And so if you look at a photon, it has a wavelength that is associated with the Planck's constant divided by its momentum. And this would be basically, this is really easily solved by relating the two relations. Energy of a photon is equal to hf, and the momentum and energy has this relation E equals pc. So if you use those, you could basically come up with this equation, and this relates very well to the double slit experiment. If you set the parameters with a specific spacing d, a slit spacing d, then you can very accurately predict the light and dark bands of the interference pattern. Now, Broglie did this thing where he said, what if we were to plug a particle's momentum into this equation versus the photon's momentum? And so if we look at a particle has momentum gamma mv, and so gamma is the relativistic term, which is going to be 1 when v is small, and then it goes up to infinity as v approaches c. And so you can look at de Broglie's equation, put a little b under there, is just the same thing, but like that. Oh, geez. And every time I want to, when I spell this in my head, I have to say de Broglie. And again, if we look at this experiment now with electrons or particles with mass, it also agrees very well with this double slit experiment. Other than just this, agreeing very well with experiment, there's a couple other things that make people warm and fuzzy about this. And so the first one is if we look at a matter wave, basically the phase is going to be equal to kx minus omega t. And so k is going to be a function of just the wavelength, or is dependent on wavelength. And then omega is going to be a function of the velocity, assuming we have lambda on the bottom. That should be t. Basically, if we use this defined as k, we can solve for lambda so h bar is just the Planck's constant with the factor 2 pi in it. And then we can also look at the frequency is equal to and this is just looking at the energy equation. So the top one's the momentum equation, and we can come up with this relationship here. E equals h bar omega. So assuming that de Broglie is correct and particles have wave-like characteristics, you could look at the velocity, the group velocity of the wave is equal to the derivative of omega with respect to k. And this is where it starts to get interesting. So this here really is only for a photon. We're looking at, these equations are for a photon, but they'll, people, what they'll do is they'll plug in these relations for W, K, and omega. And essentially they'll be E divided by H bar P for H bar, right? So the H bars cancel. And then they'll, for some reason, say, well, we can, even though we just use the relationship with the photon, we can come in here and put the kinetic energy in here, which is P squared for a particle, non-relativistic solution here. And that equals 2P over 2M, which can be simplified MV 2V. And so somebody would say, well, the velocity of the wave, the group velocity is equal to the velocity of the particle, and everybody's happy there. But I don't understand how they're jumping between the two different energies, because this is really, on the left side here is the energy of the photon, and then we plugged in the energy, kinetic energy of the particle, whatever. Another way that they'll solve this is they'll say kind of the same thing, dp, same step, and so they use, in order to go from d omega dk to get to d energy over d momentum, they use the relationship with the photon, and then they somehow convert back to the energy of a particle. And so the derivative of energy with respect to p, the momentum, is and then they can go through some magic thing here with the phase velocity and yeah, I don't know. They do a weird loopy kind of thing and they get back to v. So the phase velocity, how I understood it, didn't really make any sense because it seemed like they were doing a relationship that depended on itself. And but I guess all this to be said is that I don't actually agree that this is making a lot of sense, because really the energy of a photon is hf. And so we can say this. And so the energy of a photon with the de Broglie wavelength is not going to be equal to the energy of the particle. And so really, there's a wave part that the particle is making, but it doesn't contain all of the energy of the particle. And whatever, this could be maybe just for food for thought, but we'll move on. So the standard, the easiest way to simulate the double slit experiment is to basically, we have a slit and we're going to create two sources of wave like behavior, and both of these, so basically F1 is going to be equal to some sort of amplitude I like to be in frequency space, but the previous equation for phase was with velocity, but velocity and frequency are just related that way. So basically still the same equation. And so we have for the function 1, if this is slit 1, and then we have slit 2. And then if you just sum the contribution of those, you get this nice interference pattern, which I can show you really quick. So let's look at that. Okay, so here is just a little simulation using the equation. Now this is with the at any, like a constant time, so we don't have the time dependent here as it's not moving, but you can see we have basically the top slit has wave-like pattern emanating from the top slit, then we have wave-like pattern emanating from the bottom slit. And so when we look at the combination, when we add those together, we get this cool interference pattern, and the green spaces would be where the particle or the wave does not want to end up. And so you would expect larger zones of intensity in between the green. And so let's look at if we vary the time just for giggles. Okay, so now we have a time dependence, and so the time is just marching along and the wave is emanating outward from the top slit. The wave, now we also have the wave from the bottom slit, and the combination is just going to look like this. So we have the in between the dark spots, the green would be a wave that's moving along. So basically the dark doesn't move. It's only the spaces in between that's kind of changing. So this works really nicely. We get exactly what we'd expect from theory versus experiment. Okay, so the problems in quantum mechanics start So this is where kind of we start to get into problems with interpreting this in a real sense, because basically in order to solve this, we have a wave that's moving at v, the velocity of the particle. However, signals anything that moves in space-time, like in terms of signals or whatever, is going to be moving at c. And so this is like trying to have a sound wave when you're talking to somebody move less than the speed of sound, and we just can't support that without making some sort of probability waves or wave function collapse. So, and all of this becomes very quite hard to explain in a realistic sense. And so, and then one other like thing, like I wonder, is many of the founders of quantum mechanics did not like renormalization or the collapse of the wave function. And so I sometimes wonder if they had this huge uncertainty about this aspects of the theory and they couldn't solve it. And so the next generation just said that this is kind of how it was and accepted it. And so we just got into this state of complacence and didn't really advance the theory because we didn't know how to actually question this and come up with a better solution than what they had determined before. Now, so the de Broglie wavelength is not a characteristic of the particle, and this basically is probably obvious to somebody that teaches quantum mechanics and such and looks at this very in depth. But I like to just bring this up because it might not be obvious to everybody else. So if we look at this, we have some sort of electron gun, or let's just say a particle. We're going to have an imaginary particle that's getting shot out. And the particle is going to have velocity of 1. And the mass is going to be perfect such that when we calculate the de Broglie wavelength, it has a wavelength of 1. And then we have this detector. And this is going to be, well, interference. So this is just basically some sort of double slit experiment, but it's going to look at the way the characteristics of the wave of this particular particle and maybe measure. And if you look at, record the interference pattern, and we can do the math and say that what's measured here is going to be 1 as well. And so I'm not even putting units on this because it's just conceptual here. Now, if we then have the same thing here, bigger gun for some reason, we have velocity equals 10 for this particle. And so the wavelength is now going to be 0.1. And it's just a nice linear relationship as shown before. Now the detector is going to measure 0.1. Everybody's happy. However, if we say velocity equals 1, we're going to get a wavelength of 1. And then this detector has a velocity equal to 9. This is non-relativistic, so we're just adding velocities. Well, right, so the de Broglie wavelength is really, the result of two inertial frames interacting. So it doesn't really matter what the particle was wiggling or oscillating at before, as long as it's interacting with the other frame, and it's that interaction between the two frames that creates the interference pattern that we always see. Okay, so keeping that in mind, we'll keep on going. Now this one slide is a little bit more speculative in my opinion, so take it with whatever grain of salt that you value or something. But basically, when we look at the double slit experiment, everybody in the world is going to draw it like this, where we have the two slits with some separation d, and then where this is the and then the particles are shooting this way. Now, I would argue that they are leaving out, especially for electrons. I don't think it's as critical for photons or light experiments, but I would argue that one of the biggest things that we're taking for granted is that there is usually some sort of thing here. They call it a collimator. I don't know why, that's not, I don't know how it's actually collimating any of the signal. But what I'm saying is that this is critical because it's not a collimator, but and so what I'm arguing here is that an electron needs to start to interact with the inertial frame first to kind of start to help its wave-like properties expand out from, maybe its normal case. And so basically we're going to get this pattern. This helps to get the wave information to both slits evenly. Whereas if you don't have this collimator, I don't think the wave-like characteristics of an electron is going to be as prominent. You probably can still measure some sort of interference pattern, but I think that the introduction of this wave-inducing slit is going to increase the signal quite nicely. And I did my best to find more papers, but finding the actual experimental setup for the double slit experiment with electrons is pretty hard. But in both of these experiments. They do have a collimator. And there was a third one I found on my phone, but then it was like a link to a link, and then I lost it and I never could find it again. But yeah, so whether this is actually true or not would be for somebody to, if they could find more papers, maybe we could find an experiment where they don't use the collimator, and it'd be interesting to look at. But okay, so another just side step, but moving on. So now let's talk about how we can get the double slit experiment to work with real and physical somethings. So what does this mean? If there's a wave, then something's got to wiggle, right? We can't have a wave without some sort of oscillating motion. And the other thing is that if there is any information that is being transmitted, it has to be transmitted at c, because nothing can support a wave traveling less than c. Okay, so now assumption one. Particles are made of space-time particles, right? So an electron is really just a large collection of space-time particles in an, special or an excited state, or pinch state, whatever you want to call. And they have, there's a boundary between the electron and the medium, but it is, it's the same stuff. So they do have this direct connection. And so when the particle oscillates, then it can transfer that oscillation to the medium itself, right? So we have, maybe we just do electron. If the electron's wiggling up and down, then we're going to get a wave, and that's going to be at C. And likewise, you could also have this electron wiggling forward and backward, and you're also going to get some sort of wiggle that is moving at C. Now I think everybody loves this equation. But this is only for photons. So we're going to be making waves, but those waves don't have to follow this relationship because it's just a wave. A photon, let's see here. A photon is moving at C. So right, so a photon's moving at C, so it's indistinguishable from the wave that's also moving at C. So it's really easy to say that the quantized bit of energy and momentum is all carried in the wave, when in fact that quantized energy, that little bit of momentum or energy doesn't necessarily have to always be carried in the wave. It's something that's oscillating and carrying energy, and it could have a wave part. That doesn't mean that all of that energy is in, purely the wave part or whatever that is happening here. So really, I'll explain this more in a few slides. But ultimately, what I'm trying to say is that if the electron is moving and we have this de Broglie wavelength that we know works really well, it's really that the Planck's constant is the barrier between the small stuff and the large stuff. And so let me go to assumption 2 first. Now, assumption 2 is that if space-time is oscillating from this electron or whatever, then other electrons can feel this oscillation and they can respond. So the material that makes the double slit can persist this oscillation without the particle, right? So basically, the oscillations in space-time induce an oscillation in the electrons making in the material, the slit, and that can kind of create its own signal, right? So if an electron is going forward here, it's going to be making some sort of wave, and this is going at C. Now, this is all electrons in this that make up this slit. And so as this wave interacts with the electrons, these electrons are going to start to oscillate, and they can continue to radiate that information even once we get rid of the electron. Now this would eventually, damp out to nothing, but this signal should persist for a little bit of time, at least on the scale of the experiment. And so what we would know here is lambda, same lambda there. Whatever wavelength that is, it's the same. And this is going at C. Okay, so now assumption 3. Assumption 3 is that frequency bridges the gap. So we have an electron, and it's contained in some sort of sphere or whatever, right? And it's going to have properties such as the wavelength and frequency. And then they're also going to have this wave. And this is also going to have properties. And we're going to call this lambda C, right? Because this is a wave that's traveling at C. It's like, I also call it the light signal. It's not light because it's not a photon. It's just a wave that's being made. And so the wavelength cannot really be related between these two. However, the frequency can. So this oscillation is going to be related to the oscillation here. And what we can simply do is do a little bit of a Doppler relationship. And we're just going to ignore the relativistic stuff for now, but we'll get to it later. And so basically frequency is going to carry over between the two. Okay, so now we're going to start simulating this. Now, if we start to build up the equations, we have the wavelength of the particle is going to be the de Broglie wavelength without the gamma. The frequency of the particle is just going to be the relationship with the wavelength and velocity. The resulting wavelength of the light signal is going to be, as I wrote in the previous one. And this ultimately is just the velocity of the wave divided by its wavelength. Our frequency. Sheesh. Okay, so we have those. Again, this one doesn't. I'm not really using relativistic equations here, but it doesn't matter too much. So the slit width is equal to 4 of the de Broglie wavelength. And I'm using a relatively fast, well, let's write this. So the function from the first slit is just going to be cosine D1. Okay, so basically we're doing the first slit. We're just going to say that the particle goes through the first one. And this is going to be the light wave. You know, the signal light wave, it's not light wave, whatever you want to call it. And then this is going to be the distance from the second slit to the point of interest using the light wave length and with the frequency of the wave times t. I want the waves lengths of the particle and the light to be kind of on the same order. I'm going to pick a pretty high velocity such that we start to bring down the wavelength of the light signal as well. Yeah, so I guess, is this the right way to write it? Much, much bigger than the wavelength of the particle. And so in order to just see this on the same scale, we're going to do, you know, a good fraction of the speed of light for the velocity, which gives us a gamma 1.06. Again, I'm not using gamma for this particular simulation, so, but you'll see it doesn't matter, but we'll get to it soon. So without relativistic corrections, we have the particle wavelength to be picometers and the wavelength of light, the light signal to be 14.5 picometers. Okay, so let's look at this. Okay, so here is my simulation. We have, again, the particle wavelength is shorter than the light signal's wavelength, and you can see that. So particles coming in from the top and the light signals coming in from the bottom. Everybody that is probably familiar with this experiment before is probably annoyed that I'm trying to force the particle to go through one, but that's the whole point of this. So anyway, you can see this signal has the larger wavelength. This signal has a shorter wavelength. And when you combine those, basically we get rubbish. Now, let's just, for giggles, look at what the time dependence does, because who knows what might happen. Okay, so again, we have, this is going to be moving at the frequency of P. This one is going to be moving at the frequency FC. And when we combine them, now it's just trippy, and again, it's rubbish. However, the problem, though, is when you're doing this analysis prior, we're assuming that the waves are moving at the same velocity, but now they're not. So we can't actually use this. We have to improve our analysis because now the two, we need to sync their time essentially. And so let's look at how we're going to sync their time or synchronize their phase or whatever we want to call it. But let's look at this in a little bit more detail. We have a double slit, and we're going to be interested in some point here. I'm just going to say E is this way. So the light signal is coming in from the bottom. The electron is coming in from the top. So the particle is going to be moving along and oscillating this whole way. And so the amount of time that the bottom slit observes as it passes, as the electron goes from the start of the slit to the end of this, to this point of interest, is going to be TP. Right, simple there. And so the actual function, one, there's no position component of this because the particle is moving along with the wave. So we're only interested in the time component. And so at this point, the phase is going to change relative to the time that passes and the frequency of the particle. Now, for the second slit, these waves are going to kind of be persisting because the electrons in the slit are holding this kind of signal, oscillating with this signal. Okay, so the wave is still going to travel a distance 2p, or d2. I don't know why we got 2p, but d2. And so the phase is going to have a component of the distance that the light wave has to travel, or the light signal. And its phase, though, now is going to be proportional to the amount of time that's passed, because we're interested only in the phase when the particle is at that location. TP. Okay? And so this is the equation that we are looking at. So what does this look like? Okay, so as expected, the particle coming through the top slit is going to have another wave-like pattern emanating from the top slit, just like we'd expect. However, what does the bottom slit look now that we've synced them? Okay, the bottom slit now just looks like something curious. And it doesn't really look like there's anything to be done here. But what does it look like when we combine them? Okay, so we get some really interesting results here. Now, you can see we get kind of what we're looking for. We get these big green, bands of where we wouldn't have signal. However, if we look at, so this is showing the total of the two, for this experiment. And now I also, on this next image, is going to be just the correct solution that we'd expect. Okay, so you can see that so what we have now, correct. Now, correct. Clearly, they are not the same, and so this solution is not really correct. We've got something wrong. What could it be? Well, we assumed that the de Broglie wavelength is the particle's wavelength. Could it not be? Maybe. Let's switch that around. So, does not work, unfortunately. So now we're going to look at what if the wave that it generates is at the wavelength of the de Broglie, or the de Broglie wavelength. I said that weird. So again, we have some electron, and that's going to be oscillating. There's going to be some sort of zone of influence. I don't know what we can call this, but there's going to be some sort of zone that may, the moving frame, whatever. We don't want to get too bogged down in the details at the moment because we're going to look at this down the road. But the oscillation here, and then so this is going to be the de Broglie wavelength. And so a couple interesting things here is that, again, this does not hold. We don't know anything about the intensity of this wave other than that it's at this frequency. We don't know the amplitudes. We don't really care at this point. This wave is going to be in and this is going to make some people happy. Is a lot of the current physics is really nice because it's frame independent, and I'm trying to argue that maybe things are frame dependent, unfortunately. But we can persist. Yeah, so this is basically some sort of... Now, don't get too caught up on what this circle means. It's probably proportional to the wavelength of the de Broglie, the de Broglie wavelength, but it doesn't mean that it's all moving together. The inertial frame could be something small on the inside, but whatever. We'll have to study this more later. But what I was trying to say before is that this boundary is like a Planck boundary, right? It's between the... And so the Planck's constant is really a way for this little wiggle or whatever's happening in the electron to create a wave that has the right wavelength proportional to the momentum that is being moved, trying to be forced through space-time. And again, very probably confusing at this point for everybody, including myself. But here we go. Okay, so let's look at these parameters before we run it. This is just what we were saying, but now we're going to add the relativistic equations in here just so there's no concerns later. These equations are just the de Broglie equations. Typically, so this would be in lambda b. The frequency is just something we can do when we're looking at the a wave at the speed of light. The resulting frequency of the particle is going to be, it's the same relationship, just in the opposite direction of what we were doing before. If you ever see me use beta, beta is going to be defined by this, pretty standard. The wavelength of the particle is going to be velocity over the frequency of the particle. Just something to look at is when V is small, V, Fp, and Fl are about the same, and so the particle wavelength is going to be very small, basically. Yeah. It's interesting because this really has a velocity part, and those just both cancel, but whatever. So with this current simulation, we're going to have a wavelength of our wave. The wavelength of the light signal is going to be 6.86 picometers. The wavelength of the particle is going to be 3.43 picometers. And now the equations we're going to look at almost the same equations. Again, the particle is going through the first slit. Where Tp is equal to the distance traveled divided by the particle. Dog's whining. Okay, so, but one thing that we need to account for is that we've added this. Now we're trying to solve this accounting for special relativity. And so we are in frame, we're in the frame of the slit. Okay. And so the time, Tp, is really going to be adjusted by this. I think I do this opposite of the, Einstein's example, but just don't get too hung up on that, right? So the time is in the frame of the stationary slit. And so if this is 1 second here, we would expect, the time of the particle to have a slower clock. And so t would be 1 here. This would be some smaller fraction. Gamma is always greater than 1. And so whatever, that's just the relationship that we got. So now Tp prime is going to be Tp over gamma. And what we actually have here is this is T prime, Tp prime. And so Tp prime times Fp is really going to just be Tp over gamma times Fc1 minus Vc, and then gamma. So essentially, we can still do this because the gamma components cancel out. For that's why we kind of got away with just the simplified version up above. Anyways, let's look at the simulation. Okay, so now if you notice, the wavelength of the particle on the upper slit is quite a bit smaller than the previous one. Any sort of weird coloring or shading that you're seeing here is just that there's a little bit of aliasing because you can only do so small of grids before the thing takes too long to run. And so we got the top slit is where the particle is, short wavelength. The bottom slit is where the light signals coming through adjusted to the time of the particle, and then the resulting combination of the two. Ooh. And now if we compare it to the correct solution, you can see that we get these green, the dark spots line up very well between the two. Great. Cool. So what this is saying is that the de Broglie wavelength is the actual wavelength of the wave passing through space-time. It's not the wave of the particle itself. So let's just look at these equations that we just derived and see what else there are other interesting aspects. And so the top plot here on the left is going to be just wavelength, and you can see, sorry. Oh my God. We're just, so as wavelength, so red is the wavelength of the particle, green is the wavelength of the light signal, and so you can actually see that the wavelength of the particle has this really nice flat line, which I don't know if it means anything, but you can do the math if you want, and essentially what you get here is the wavelength of the particle simplifies to 1 plus beta. Again, beta is V over C. And so this is just a nice kind of linear curve. And then the frequency of the particle, again, is in red. The green is the signal. And when the Doppler correction is very small, they're pretty much the same. As you speed up, there's more and more of a split. And if you really wanted to know what that was, the frequency of the particle is going to be CMV over H. Okay. So whether this is useful, this is just more interesting here. Okay, now let's go even one step further and really go into the weeds maybe. But we're going to look at this same thing with Einstein's Doppler. And what I mean here is that we have this we got a particle. Gives us an electron. Doesn't actually matter. So now the interesting thing here is, right, Einstein's equation for relativistic Doppler effect should actually look something like this. So the wavelength of the particle is going to be the wavelength of the source, because we're in the rest frame. Times cosine theta in the source, right? And so basically this is going to be theta s. Now, just some little thing for reference is, for our simulation, L equals it's a pretty small grid because I had to do really small grids, so I couldn't really cover that much distance. And so this, the little zone that we're looking at is very small relative to what you'd expect on a, if you did this in real life, you'd use some sort of lens to diverge the electron beam to get the interference pattern, but your scales are going to be much larger than 20 nanometers. And so what we know, if L, let's just say L goes way, way bigger than 1 or 0, however you write that, basically theta is going to converge to 0, and so this little term cosine of 0 goes to 1. And so essentially what's nice is that when you're looking far away from this, it's going to basically get the same solution we saw before. But we can just still look at what it looks like on the right next to the slit. So we'll do that right now. Okay, so now this one is a little bit different. Before I start it, the top slit is going to be assuming the electron goes through the top, or this first image is the electron going through the top and the combination of the light signal coming through the bottom. The second image is going to be the same thing, however, the electrons coming through the bottom slit. And it's the totals for both, the total contributions of both slits. And so we get this interesting behavior here. So again, this is for electrons coming through the top slit. This is for electrons coming through the bottom slit, accounting with using Einstein's relativistic Doppler equation. And so essentially what, if you were to imagine an electron coming through here, these zones are going to be zones that it doesn't want to, it's going to be maybe like zones of higher pressure, whatever you want, however you want to interpret it. But electron is going to come through here, maybe it's coming straight and it's going to get pushed a little bit, and every time it gets pushed, it's going to have more, of a vector in that's aligned with these brighter bands. And so, this is kind of with the guiding wave of other theories. But interesting enough, when you combine this, you get quite the mess. But when you look at the actual solution so here is the dead spot, and we have a little bit, at least the bands line up, and I would expect that as you did this over, instead of 20 nanometers, you did this over 20 centimeters, these green bands are going to converge to the same answer as we see in the previous case. So a little bit messy. I could take this off but I didn't think it'd be, I could extend this for a longer range, but didn't think it would be, see anything unexpected there. So I think we're going to wrap this up now. Okay, so reviewing, the main point that we have here is spell corresponds, right? Now, immediately people are probably going to start to be, well, there's a lot of reasons people might be upset with this, but like you can look at some of the early solutions for the hydrogen use this relationship that the electron is moving at the de Broglie wavelength. It's trapped in some sort of potential. We're just going to have to look at that in more detail. But the big question though is what is kind of less crazy? They're both kind of hard to maybe stomach at this point, but our existing interpretations, we have many worlds, which seems, pretty outlandish. We have instantaneous collapses of the wave function. So we have, a particle that's spread out evenly through space-time, and then suddenly it's in one space. That's what Einstein called spooky action at a distance. He didn't really like that. We don't know what triggers this collapse or what level of like measurement until this, gets this wave function goes from totally spread out to a singular point. And we have this kind of non-physical wave. However, if we look at this interpretation, we have a physical wave, which space-time oscillates. We know we get gravitational waves, we have electric fields and stuff. It's not too unreasonable to assume that the particle could create waves in space-time. An electron creates fields. So why can't it cause little oscillations? And also we depend on the slit carrying the space-time waves inducing oscillations in other particles. And so, those are kind of the three main things that we need to accept in order to get this double slit interpretation to work. And I personally think that this one's not as scary as the one on the left. Okay, so next steps, I want to, I have this presentation on dark matter close, but there's this thing about ideas versus theories. Ideas always work because they rely on the physics in your head, and that physics doesn't actually match reality. So I have this idea, I'm working on the math. It's getting closer. I just want to make sure I'm close enough that people will accept it closer to a theory than an idea. I know it's pretty far away from perfect theory, so we'll just have to get a little bit closer. I'd also like to talk about more of this, like the particle wiggling and what we need to do to make that happen, because it's still, it is not at all easy or trivial. And then I have all these other kind of more fun-based, they're just purely ideas, but more Gedanken experiments or whatever, we can go there. So probably one of those for the next one, but I'm going to try to get more videos out. There was kind of a long gap in between. But the fun thing about the wiggle is if you were to take some sort of sphere that is proportional to the de Broglie wavelength, and you wiggle it according to Fp, you can actually, and it's still moving, if you wiggle this particle, you have some sort of function, force function over this range, you can actually generate this wavelength that moves outward at C, And what's really fun is that you almost get a smooth trailing of space-time, right? So basically you'd have some sort of force function oscillating at f of p and supplying energy into the space-time particle over this sphere as the electron's kind of moving along, and you get this really cool behavior. And I'm going to show that in a later one, but I'm like only halfway through there, so we still got a lot of work on that one, so that might be a wait. But anyway, thanks for your interest. I hope that this will at least inspire some new thoughts, and maybe we, new ways of looking at the physics that we're currently dependent on. And so until next time, yeah, thanks again. Like and let me know if you have any comments.